In this problem, we're going to try to figure out the expression for the Hermite polynomial for n equal to 5 and n equal to 6. So recall that the Hermite polynomial features in the solution to the Schrodinger equation, right here at this very point. So this is the solution, and then inside we have this Hermite polynomial squeezed in the middle. So also recall that for the solution to the Schrodinger equation, xi of y, in our earlier derivations, we let that this be equal to h of y, some function times e to the power of negative y squared over 2. So h of y is going to be equal to this infinite series. And you can see a bit of similarities between these two expressions. So here you see that you have a bunch of constants multiplied by a polynomial multiplied by this e term. And here we also have this e term multiplied by a polynomial. So if we can figure out what h of y should be, then we would be able to deduce what the Hermite polynomial should be. And in this case, we're going to first focus on h5 of y. So this is going to correspond to the case where n is equal to 5. And when I say the case where n is equal to 5, that corresponds to the case where the energy level, as is given by this expression. So this is going to be the case where the energy level is going to be equal to the case where you substitute n equal to 5 to this expression. And it also corresponds to the case where, once again, let us write out the recursion formula. So if you recall this recursion formula that was featured in our derivations, when I say n equal to 5, this is going to also correspond to the case where this recursion formula is going to stop when j reaches 5. So this is going to be the case when n equal to 5. So when j reaches 5, then this recursion formula is going to stop. So we're going to try to use this recursion formula to deduce what these constants should be. So this recursion formula gives us the relationship between these constants over here. And then once we derive some terms, we would be able to deduce what the expression for h of y should be, and that would in turn allow us to deduce what this Hermite polynomial should be. So let's start with the first case where n is equal to 5. So right now we're going to set our sights on finding what h of y should be for the case where n is equal to 5. So I'm choosing the recursion formula to stop when j reaches 5. So I'm going to start off with some constant a1. So I don't know what a1 should be yet, but for any value of a1, I'm able to deduce what a3 should be because of this recursion formula. So I can just substitute j equal to 1 in this case. So n in this case, I've chosen it to be equal to 5, and then j starts off at 1 times a of 1, and then for the denominator I get 1 plus 1, so it's equal to 2, and then 1 plus 2, that's equal to 3. So these cancel out, and then for the numerator I get negative 4 divided by 3 a1. So this is the relationship between a3 and a1. And now I can move on to the next step. I'm going to find what a5 should be. So once again, I'm just going to substitute it inside this recursion formula. N is equal to 5 as we've chosen, and here we've reached j equal to 3. So minus 3, and then for j equal to 3 we get 4, and then here we get 5. And then we're going to multiply this by a3. So with a bit of manipulation you can see that this is equal to 2, so these all cancel out. So I get negative 1 over 5 a3. And a3, as we found, is equal to this expression, so I can now express everything in terms of a1. So it's just 4, and the denominator becomes 15 a1. So this is the expression for a5. And as you can see, if you move on to find what a7 should be, so if you observe the recursion formula a7, we're going to have to use a5 to deduce what a7 should be. So n is equal to 5 as we've chosen, and here we see that we've reached j equal to 5 already. And you get 5 minus 5, which is of course equal to 0. So multiply this by a5, and then it doesn't really matter what we have in the denominator because this is already equal to 0. So a7 is just going to be equal to 0. And then all the subsequent terms, a9, a11, and all the a's with an odd subscript, they're all going to be equal to 0 because you're just going to have some term multiplied by 0. And then in order for our solution to be normalizable, so we've already figured out the constants with an odd subscript, but for the even subscripts we still haven't figured these out yet. And it turns out they have to be equal to 0. So a0, a2, a4, and so on, they all must be equal to 0. because otherwise there will be no way to stop these constants with an even subscript from generating further and further numbers, and then in the end this will become a solution that will not be normalizable. So it has to be the case where all these constants are equal to 0. So we come to the conclusion that, so first of all, we know that h of y is equal to this infinite series, and then we've also found all the constants. We found, so we don't know what a1 should be, but for any given a1, we know that a3 is going to be equal to negative 4 over 3a1, and then a5 is going to be equal to 4 over 15 a1, and then all the rest of these constants, they're all going to be equal to 0. So what this means is that h of y is going to be equal to a1 times y plus a3 times y to the power 3 plus a5 times y to the power 5, and all the other terms, they're all equal to 0 because the constant is going to be equal to 0. And now I can just substitute the expressions that we found. So it's 4 over 3 a1 y to the power of 3, and then a5 we have 4 over 15 a1 y to the power of 5. So now we can do a bit of manipulations. Let's just pull out the constants first. Pull out the a1. So this a1 should be gone. So y to the power of 3 plus 4 over 15 y to the power of 5. So you see that this looks pretty much like what we have over here, this section over here. So in order to find h5 of y, we're given a clue. We're given that the coefficient of the highest power is equal to 2 to the power of n. So in this case, n is equal to 5. So if, I'm going to have to move some of the constants outside in order to construct our Hermite polynomial. And then we can use this by using the clue that the coefficient of the highest power, so this is the highest power, the coefficient is equal to 2 to the power of n, and in this case n is equal to 5. So the coefficient of y to the power of 5 is equal to 2 to the power of 5, which is equal to 32. So let's try to move some of these fractions outside so that we get 32 here for the coefficient, and when we do that, this entire polynomial will be the Hermite polynomial that we're looking for. So our first step is that we could move we can move a 15 to the outside, so we get 15y, so it cancels out, you get 20y to the power of 3 plus 4y to the power of 5. And then now in order to push this to a 32, I'm going to multiply an 8 inside the polynomial. So this 8, I'm going to move it over here, and it's going to combine with this 15, so 15 times 8, that's just equal to 120. And this 8 in the numerator is going to be moved inside this bracket. So I get 120y, so 8 times 20, that's 160y to the power of 3, plus 32y to the power of 5. And there you have it. This is the polynomial where the coefficient of the highest power is equal to 2 to the power of n. So this has to be our Hermite polynomial. So this term here that I've boxed is equal to h5 of y.